Welcome. Let's look at doing some applications of exponential logarithmic functions. So we're going to start here with a decreasing population problem. So it's an overfished area. A certain fish is decreasing, or the amount of the catch is. 7 years ago, there were 3,000 fish. Now there are 870, and that's 7 years later. What we're going to do is write an equation to model this. And then we're going to see when will 10% of the fish be left, but when will there be 500? Notice the difference between the two questions. One is a percentage and one is a number. Then we'll need the equation to answer both of those. Now, the information that we're given tells us two things. At the beginning, in the 0th year, there were 3,000 fish. 3,000 fish. In the 7th year, there are 870 fish. So we have here already 2 points. We were graphing this, and that means we are something like this, and then it's gone down. So has it gone down a straight line? Is it like this kind of a curve? Is it like this kind of a curve? So what we don't know which way it's going. Okay, but we know it's exponential actually, and an exponential function goes like this. A decreasing exponential function goes like this. So that means it should be this kind of a look. So if so, I'm going to erase the ones on here we wouldn't use. It means it's going to be going like this. So we have a 0 and 3,000, and somewhere here in the 7th year we have 870. This we need the equation for. And that's what we're going to do. Well, there's a formula for this. Formula for this is A equals P E R T. So the amount at a certain time, the A and the T, well, the amount at a certain time is based on that time and a rate, and the original amount, P, is the principal amount. So we're going to fill in these parts. So to make the equation A, we're going to do A equals the original amount, 3,000, ERT, and then we're going to apply that point that we know exists, 7 and 870. So we'll say that 870 is equal to 3,000 ER times 7. That means the only variable here is R. And what we need is the rate at which it's going down. So the equation we're looking for, we need R, almost like we're finding a slope. So when it was a straight line, you could find the slope by using the rise over the run, or the y minus y divided by x minus x to get the slope of the line. Here, what we need are 2 points to enable us to find the rate using this formula. So think of the rate as a slope. We need the one that's specifically for this equation. Well, that means we now need to basically solve this stuff. Divide by 3,000. So we're trying to get to where we're solving for R. We want to get an R equals. Right now, dividing by 3,000 gives us about 0.29 is equal to E to the R, or call it 7R. The way that we get rid of E is to do natural log. 0.29 is equal to natural log of E to the 7R. So this part cancels itself out. And we have 7R equals natural log of 0.29. Let's divide by 7. So we have R equals natural log of 0.29 divided by the number 7. R is approximately, when you put that in the calculator and you go 4 decimal places, negative 0.1768. That's a very important number. And what we do now is we put that into the basic formula. The amount is equal to original 3,000, like the principal amount of money, E, and then negative 0.1768 T. So if we were given, well, and now I box this. If we were given the amount of time, we could find the amount of fish left. If we were given the amount of fish, we would be able to find the time that it took for it to get down to that low. Okay. Now let's analyze something about this rate. R equals negative 0.1768. First, this means going down, decreasing. Second, move this over, and it's 17.68%. So it's almost 18%. That's how much a loss is each year of the population. So if the fish had started with 100 at the beginning, that means there were only 2 left after the first year, and then 18% less the next year. So that's why this number is very important. It determines the actual amount of decrease, the actual percentage of decrease each year. Okay, so that is A. We just did that in equation. Now our job is to find when is there 10% left. So we're going to use that equation here. P, A equals 3,000, E negative 0.1768 T. Okay. So if the percent, it's 10%, that means that the amount, well, I'm thinking of the original, 10% of 3,000 is 300. So that means it was 300 left equals 3,000 E negative 0.1768 T. So that's what we're looking for, is 10% when there was originally 3,000, which means we don't know the amount of time, but we know the amount's 300. So we put in that amount of 300. When you divide both sides by this 3,000, we actually get 10%, or 0.1 is equal to E, the negative 0.1768 T. We will need to apply natural log to both parts so that this will be able to cancel out. So now we're at a natural log of 0.1. 0.1 is equal to negative 0.1768 T. Divide by that whole thing, and we get that T is equal to natural log of 0.1 over negative 0.1768. And when you put in that calculator, it comes to approximately 13. So that means that it's approximately 13 years. To get down to 10% of the amount of fish left. So 13 years in particular. Now let's take a look at the next part, C. C is in how many years will there be 500 fish? Let's take the formula again. The amount is equal to 3,000 E, E negative 0.1768 T. We want to know when the amount is 500 fish. That makes this almost the same kind of problem as the last one. 0.1768 1768 t. So if we divide both sides by 3,000, we get 1/6. Keep it that way for a moment in order to not have to round and lose numbers. So we're going to do the same natural log on both sides. And when we do and divide by that number, we get that t is equal to, I guess I'll keep it on side here. We have the natural log of 1/6 divided by -0.1768 is equal to the amount of time. So when you plug that into the calculator, t is approximately 10 years. I believe it's 10.13 something. 10 years to get down to only 500 fish out of 3,000. Wow. Okay, so that's the first problem. What you see is using this formula, and we'll use that one or other ones like that for many others. Now, the second problem is similar, but we're going to do a slightly different formula. Okay, the world's population in 2000 was about 6.124 billion. In 2005, it had reached this amount. So write an equation to model the world population growth based on these changes from 2000 to 2005. What is it this year? And when will it be 8 billion? Well, it's actually about to be 8 billion. So I think I should change that number here. Well, let's do that. I'll use the calculator and we'll figure out this one. If, say, it would be 10 million people, because we have noticed that this is beginning of 2023, and we're at about 7.9 billion people in the world right now. And I just read it recently. We're going to use that the function based on time is equal to the original amount, or an amount at a certain date, times e to the kt. And it's a plus or minus kt. Okay, very similar to the other proof, but it's actually about the same as the last function, except that here we're specifically going to use the letter k instead of a rate, although it actually is a rate. So let's take the points that we have here. At the beginning, at the 0th time, it was 6.124. 5 years later, it's at 6.515. So that's in billions. So let's use those things. First, this is the A. So the function based on time is equal to 6.124 e to the kt. Now I'm going to use this one. Okay, so the result, 6.515, we'll leave the billion out of it for now, is equal to 6.124 e k times 5. So now, dividing by 6.124 on both sides, gives me the number 1.0638, going 4 decimal places, is approximately equal to e to the 5k. Well, this is where we apply natural log to both of these, and that cancels that out. So we have 5k is approximately 1.0638 divided by, so k is approximately 0.0124. And if I move the decimal over, it's about 1.24% increase in population every year. However, we're going to use that to put it back into the formula. So we're going to say that the function of t is equal to 6.124 e and 0.0124 t. That is the equation that's asked for in part A. All right. Now let's do B and C using that formula. What is the population this year? Okay, so let's do 2023. That means from 0 to the 23, that means it's 23 years. And so we'll use that in the formula here. Okay, so for B, the function based on time, actually, the amount of time we know, the function based on 23 years is equal to 6.124 e, and then the amount of time is 23 times the 0.0124. So it's simply a matter of doing the calculations for this function at 23, and I'm going to put that in the calculator. 6.123 times letter E, and then up in the top of it, it's 23 times 0.0124. Okay, so I'm following this order in the calculator. Okay, and that gives me 8.143, round to about 38. Okay, and that's in billions. So that's actually 8.1438 billion people. Probably at the end of the year, possibly at the middle. I haven't actually thought about what it means with 23. But we're very close to getting to that number now. So sometime during the year of 2023, the population is going to go over above 8 billion. By the end of the year, at least reach this 8.1438 billion people in the world. Now, let's take a look at C. So for C, determining for 10 billion people, in what year will it reach 10 billion? Okay. So 10 is an amount. Okay. So we would say that 10 is the amount that we're reaching. We'll make it in billions total now. 6.124 E 0.0124 times T. T is the thing we're trying to find out. So if we divide by 6.124, then we'll apply the natural law. So 10 divided by 6.124 is 1.6329 is equal to e to the 0.12, whoops, leave that the 0 needed in there, 0.124 t. So we will apply natural log to both sides. That will go away. And so now that means we're left natural log of 1.6329 is equal to 0.0124 t. Let's divide by 0.0124 now. 24. And so that cancels out. T is equal to this, and put it in the calculator. Okay, and I'm going to put that in right now to find out. 1.6329. That's the log of that. Natural log of 1.639 divided by 0.124, and it's approximately 39.550. So the significant part of that is about 39.5. So it's 39.5 years after the beginning, which was 2000. So that means it would be during the year 2039 to reach 10 billion people. So we have our answers for this problem. The equation with correct K, 8.14 billion in 2039 to reach 10 billion people. Let's take a look at a different problem now. Next two problems are similar. This one's a half-life problem. Okay, I'm going to show I get the right page online. So we're going to use the formula. Okay, draw this line out. So the function based on time is equal to AEKT. So the half-life of sodium is 2.6 years. You write an equation of decay for sodium 22. Well, we're given not the same info we were given in the others. We're only told that the half-life is that. It takes that long. So that means that half the amount of time, well, or at the 2.6 mark, you have 1/2 of the original amount. 1/2. We have no idea how much that is, but we can plug that in here. So the function, so if the time is 2.6, this is 1/2 A. 1/2 A is equal to AE, and 2.6 times K. So we're going to be figuring out what K is. But right now, here's the first key. The first key is recognizing that half-life, this idea of half-life, means it's 1/2 of A, whatever A was. Next is a simple thing we can do with calculations. Cancel out the A's. So that leaves us with 1/2 is equal to E raised to the power of 2.6K. Now you see we're back to where we were in the other problem. Just apply natural log to both top and bottom. Okay, so I get the natural log of 0.5 is approximately equal to 2.6K. Divide by 2.6. Okay, and that means that the K is approximately, or very close to, negative 0.2, and then a whole bunch of sixes here, 3 6s. Okay. And I'm going to divide by that to see, get exactly that. Oops, I did something wrong with the calculator. So natural log of 5 and divide by that 2.6, and we do indeed get this number. Okay, natural log of any number less than 1 will result in negative, by the way. So I knew it was supposed to be a negative there. Let's put that back into this formula. So the function based on time is equal to, well, A, we have to know what the original amount would be. E, negative 0.2, and all the 6s, T. So this is our equation. Now let's do the second part. All right. So for part B, how much is left by percentage after 8 years and starting with 20 grams? So that's our starting amount that goes in as the A there now. So we had to say that much there. So what we have is amount is equal to the A, the original amount, 20, E, with e to the power of KT. And we want to know what years. 8, K. Well, we know what the K is. Okay, let's put it in the C there. 8 times negative 0.2666. And so we need to simply calculate that. Calculate P is e to the power of that times 20. So that means the amount is approximately 2.3701, which means the answer is about 2.4 grams of sodium. Okay, let's get that in. And then C, how many years to get down to 10%? Oh, remember the formula, function of time is equal to the amount E negative 0.266 T. So 10%, okay, remember, actually, you should say here, we're starting again with 20 here. And so 10% is 0.1. So we'll actually do 0.1 is equal to 20 negative 2.666. Oh, how many? Oh, I didn't do the there. Well, right. It was 0.2 and then 3 sixes. And the T, we don't know how much time. That's what we're trying to find out. So we divide by 20, and that gives us 0.005. Equals e to all the stuff up here, negative 0.2, the sixes, and T. T is what we're trying to find. So that means apply natural log to both top and bottom, or to one side and the other, I should say, and that cancels out. So we have the natural log of 0.005 is equal to negative 0.2, and all those sixes T. So here, though, since we're dividing by it, we have to divide up the other side by it. So T is approximately 20 years. Okay, and then that's because it's 19, comes out as 19.73 years. So we'll call it 20 years that he has to serve. Oh, okay. Oh no, this was the sodium one. So it takes 20 years for the sodium to go down to 10%. To get to 10%. So notice these formulas and the way we use them is pretty much the same in all the types of problems.